Hello everyone. Today we are going to understand the concept of beta function and then we are going to take certain examples on beta function. So our today's topic is beta function. Let us take first definition of beta function. Whenever we want to take definition of beta function, we have to take two numbers m and n. And first of all, we are going to study the notation of beta function. So beta function of m and n is denoted by this symbol beta in round bracket m comma n, and mathematical definition of beta function is in the form of definite integral. So beta mn is equal to integration 0 to 1 x raised to m minus 1 multiplied by 1 minus x raised to n minus 1 dx. Values of m and n must be positive, means greater than 0. So this is called as definition of beta function. Whenever we say that beta mn, m and n appears in the index of these two terms with minus 1 along with m and n. So whenever we say that beta mn, remember x raised to m minus 1 and 1 minus x raised to n minus 1 must be there with the limits of integration 0 to 1. Beta function is also called as Euler's integral of the first kind, and gamma function is called as Euler's integral of second kind. Now we will take properties of beta function. Number one property that we are going to take, that is beta of mn is equal to beta nm. What it means, if you interchange the number m and n, doesn't make any difference. For example, if I write down x raised to n minus 1, 1 minus x raised to m minus 1, final answer is not going to change, and therefore beta mn is always equal to beta nm. Let us take property number 2. Integration 0 to 1 x raised to m multiplied by 1 minus x raised to n dx. So what is the change with the definition? Now in the index, minus 1 is not there. So if minus 1 is not there, we have to do the adjustment in the index. We have to add 1 and we have to subtract 1. So instead of m, we can write down m as m plus 1 minus 1. We can write down n as n plus 1 minus 1. And therefore, we can directly write down answer as beta of m plus 1 comma n plus 1. Now let us take alternative definition of beta function. An alternate definition of beta function is now in terms of definite integration within the limits 0 to infinity. So let us see this definition. 0 to infinity, x raised to m minus 1 upon 1 plus x raised to m plus n dx. Whenever we say that beta mn, m appears in numerator with x raised to m minus 1 as well as in the denominator, but n is present only with m plus n there in the index of denominator. This is called as alternate definition of beta function. Let us take property number 4, very important, that we require while solving the examples. Whenever we get the answer in terms of beta function, it should be converted in terms of gamma function and then into a final answer. And therefore, this is the most important property whatever we require while solving the examples. So relation between beta and gamma function is given by beta mn is equal to gamma m into gamma n upon gamma of m plus n. So these are the 4 properties are there. Let us take now 5th property. So property number 5, gamma of p multiplied by gamma of 1 minus p is equal to pi upon sine of p pi, where value of p should lies in between 0 and 1. This is also one of the important property that we require while solving the example. Number 6, beta function in terms of trigonometric function. Original formula of beta function in terms of trigonometric terms is like this: 2 times integration 0 to pi by 2 sin raised to 2m minus 1 theta multiplied by cos raised to 2n minus 1 theta d theta. Now, whenever we want to convert trigonometric terms in terms of beta function, this is a quite complicated formula. So, we are going to make it simple by doing a substitution. So, let us do the substitution. 2m minus 1 is equal to p, and therefore we can say that m is equal to p plus 1 by 2. Similarly, we can go for substitution of 2n minus 1 is equal to q, and therefore we can say that n is equal to q plus 1 upon 2, and therefore this formula will get modified into, so integration 0 to pi by 2 sin raised to p theta into cos raised to q theta d theta. So whenever we solve the example, we need this particular form of this formula, and that's why here sin raised to p theta and cos raised to q theta are written within the limits 0 to pi by 2. In original formula, there is 2 along with integration. So these 2 will get shifted to other side. So formula will become now 1 by 2 beta of p plus 1 by 2 comma q plus 1 by 2, because values of m and n are there in terms of p and q. So this is property number 6. Now second one is duplication formula. This formula is useful for certain examples. So remember this formula as well. Gamma of m into gamma of m plus half is equal to root pi upon 2 raised to m minus 1 gamma of 2m. So this formula is called as duplication formula. So we have studied properties of beta function. Most of the properties we require while solving the examples. So how these properties can be used, we will see in the form of different examples. Let us take examples. So example number 1, evaluate integration 0 to infinity dx upon 1 plus x raised to 4. So here let us take the solution. Let us assume that given integral be equal to capital I. So therefore I is equal to given integration. Now how this can be solved? You must know the concept. Whenever integration contains the term 1 plus x square or 1 plus x raised to 4, we are having a standard substitution in terms of tan, as well as from 0 to infinity we come to know that substitution must be in terms of tan, because we know that tan pi by 2 is equal to infinity. We have to adjust the value of tan in such a manner this 1 plus x raised to 4 becomes a standard identity of tan. What is the standard identity of tan? 1 plus tan square theta is equal to sec square theta. And therefore, from this we come to know that we have to do the substitution for x square. So let us do the substitution in terms of x square. So if the integration in terms of a square plus x square, we do the substitution regarding tan as I told you earlier. So here a is equal to 1 and also integration contains x raised to 4. So let us take substitution x square is equal to tan theta. Now we have to take the value of x by taking square root on both sides. So therefore x is equal to root of tan theta. Let us find out dx. Dx is equal to derivative of root of tan theta. First of all, take the derivative of root 1 upon 2 root of tan theta. And as per chain rule, derivative of tan theta is sec square theta d theta. Now next is we have to see that what is the value of 1 plus x raised to 4. So 1 plus x raised to 4 is equal to 1 plus tan square theta. And therefore we get sec square theta. So that exactly I was talking. So we have to do the substitution in such a manner that this entire term gets replaced by identity. So 1 plus tan square theta, in short, value of denominator is now sec square theta. Now we also have to change the limits of integration. That is, at x equal to 0, we get tan theta equal to 0, and therefore theta is equal to 0. At x equal to infinity, we can write down tan theta equal to infinity. We know that tan pi by 2 is infinity, and therefore we get theta equal to pi by 2. So therefore now let us take new limits. Integration 0 to pi by 2. Replace that 1 plus x raised to 4 by sec square theta, and dx by its corresponding term sec square upon 2 root tan theta d theta. Observe that sec square theta gets cancelled. We can simplify further, taking 1 by 2 outside the integration, and then we can write down tan theta in the numerator as quat. So root remains same. So it is root of quat theta d theta. Let us do the simplification now. So I is equal to outside term as it is. We know that quat means cos upon sine, and therefore we can write down cos upon sine. And because of root, we can simplify that cos raised to half theta upon sine raised to half theta d theta as it is. Now we have taken a property in terms of sine raised to p into cos raised to q, and therefore we must have sine and cos both the terms in the numerator, and therefore we are going to do now adjustment over here. So 1 by 2 as it is, integration 0 to pi by 2, we can write down sine raised to minus half theta by taking sine to the numerator, multiplied by cos raised to term as it is. Now observe clear cut, as per the standard formula, sine raised to p into cos raised to q, value of p is minus half and value of q is half. So using standard formula, 0 to pi by 2 sine raised to p theta multiplied by cos raised to q theta d theta is equal to 1 upon 2 times beta of p plus 1 by 2 comma q plus 1 by 2. Let us put the value of p as minus half and q is equal to half. So let us do the substitution in this particular example. So therefore we can write down I is equal to 1 by 2 as it is, and then there is 1 by 2 in the formula as well. So multiplied by 1 by 2 beta of minus half plus 1 upon 2, 1 by 2 plus 1 upon 2. So just by replacing p by minus half and q equal to half, we are going to simplify it further. 1 by 4 into beta of, so it is minus 1 by 2 plus 1 is 1 by 2, 1 by 2 upon 2 is 1 by 4. Similarly, second term can be simplified, and that is 3 by 4. Again, we have to use the property, that is converting beta function into gamma function. So using relation between beta function and gamma function, beta mn is equal to gamma m into gamma n upon gamma m plus 1. So gamma m into gamma n means gamma 1 by 4 into gamma 3 by 4, because we found out value of m as 1 by 4 and value of n as 3 by 4. So substituting these two values in the standard formula, so we get I is equal to 1 by 4 as it is, gamma 1 by 4 gamma 3 by 4 upon gamma of 1 by 4 plus 3 by 4. Observe that 1 by 4 plus 3 by 4 is equal to 1, and therefore we are going to simplify this term in this manner. Now gamma 3 by 4 can be written as gamma of 1 minus 1 by 4, and denominator we are having gamma 1. Why we have written that in terms of 1 minus 1 by 4? Again we are having one more property, and gamma 1 is equal to 1 naturally. So using the relation gamma p into gamma 1 minus p is equal to pi upon sine of p pi. Observe that it is in the form of gamma p into gamma of 1 minus p, where value of p is 1 by 4. And therefore, we can write down gamma 1 by 4 into gamma of 1 minus 1 by 4 is equal to pi upon sine of pi by 4. Sine pi by 4 is root 2 and value of p is 1 by 4. So simplifying pi upon 1 by root 2. So final answer is pi root 2. So just substitute the value of this numerator in the equation of I. So I is equal to 1 by 4 as it is and pi root 2 is there in the numerator. And therefore we can say that final answer of this integration 0 to infinity dx upon 1 plus x raised to 4 is equal to pi root 2 upon 4. So this is the example in which we use number of properties. So you have to remember all the properties properly so that we can apply that properties in the example. Let us take now example number 2. Show that integration 0 to infinity x raised to m minus 1 upon a plus bx raised to m plus n dx is equal to 1 upon a raised to n b raised to m beta of m comma n. Now here we can observe that integration limits are 0 to infinity. In numerator we are having index as m minus 1 and denominator m plus n. It's very clear from this we have to use alternate definition of beta function. So let us start with LHS. How to solve? Let us see one by one. So by alternate definition of beta function, that is beta mn is equal to integration 0 to infinity y raised to m minus 1 upon 1 plus y raised to m plus n dy. We have written definition in terms of y for sake of convenience. Remember that in definite integration, variable is never important. And therefore, we can write down the definition in terms of x, in terms of y, in terms of t, or any other variable, whatever we want. Now we can start with the LHS. Before starting with LHS, we have to do the substitution. That is bx is equal to ay. Why we have to do the substitution bx equal to ay? Because this denominator should be in the form of 1 plus y. And therefore, we can have a plus bx is equal to a plus ay. So to convert that LHS denominator in the form of definition, we have done this substitution. Observe that if you take a common, we get a into bracket 1 plus y. So this 1 plus y is our required term. And therefore, this substitution is made. Let us see the value of x now. Bx is equal to ay. So we get x is equal to a upon b into y. As well as we have to find out value of dx. Dx is equal to a upon b into dy. Now we can see that limits of this integration remain same because at x equal to 0, we get y equal to 0. At x equal to infinity, y equal to infinity. So let us substitute in the LHS. So LHS is equal to 0 to infinity x raised to m minus 1. Now instead of x, we have to write down a upon b into y. And denominator value is a into 1 plus y, keeping all indices same. So a upon b, y raised to m minus 1, a into bracket 1 plus y raised to m plus n multiplied by dx, that is a upon b into dy. Now we have to use laws of indices to simplify this entire term. We are going to take constant term outside the integration. First of all, we can see a upon b raised to m minus 1 is a constant term, as well as a upon b is present, and also we can take this a raised to m plus n common. So therefore, LHS is equal to a upon b raised to m minus 1 we have taken common. Take this a upon b also common. Also take a common from the denominator. And now write down remaining term integration 0 to infinity y raised to m minus 1 upon 1 plus y raised to m plus n dy. So see that whatever integration is there, that is nothing but definition of beta function. And therefore, we just have to simplify these constant terms using laws of indices. And here we already got beta mn. So next step, LHS is equal to simplifying the term a upon b raised to m minus 1 into a upon b. Minus 1 plus 1 gets cancelled and we get a upon b raised to m. Also, second term, as it is time being, multiplied by alternate definition of beta function, and therefore that integration is equal to beta mn. Next step, now we can separate all the indices. We can write down a raised to m upon b raised to m as well as a raised to m into a raised to n using laws of indices. Beta term as it is. That is equal to final answer. Clear cut we can see a raised to m gets cancelled. So LHS is replaced by original question and that is equal to 1 upon a raised to n b raised to m multiplied by beta mn. So in this manner we have proved this. Example number 3. Evaluate integration 0 to infinity x raised to 9 1 minus x raised to 5 upon 1 plus x raised to 25 dx. Observe that limits are in the form of 0 to infinity. It means that again we have to use alternate definition of beta function. So let us assume that given integral b equal to I, we are going to expand this bracket. So first of all, let us rewrite down this I. Integration 0 to infinity x raised to 9 bracket as it is, denominator as it is into dx. Let us expand the bracket. So I is equal to integration 0 to infinity x raised to 9 minus x raised to 14 upon 1 plus x raised to 25 dx. Now next is we are going to split it further. So integration 0 to infinity x raised to 9 upon 1 plus x raised to 25 as well as second term in the form of other integration 0 to infinity x raised to 14 upon 1 plus x raised to 25 dx. Now see alternate definition. So what is alternate definition of beta function? We are having x raised to m minus 1 in the numerator. And therefore, as far as first term is concerned, this 9 must be written as 10 minus 1. And here 14 must be written as 15 minus 1. And whenever we are getting value of m as 10, in first case, index 25 can be written as 10 plus 15. For second, whenever we write down x raised to 15 minus 1, we get the value of m as 15. And therefore, this 25 can be written as 15 plus 10 like this. So integration 0 to infinity x raised to 10 minus 1 upon 1 plus x raised to 10 plus 15. And then second, integration x raised to 15 minus 1, 1 plus x raised to 15 plus 10. And now we can write down next step as we can use alternate definition of beta function and then we can write down I is equal to. Observe that this is in the form of beta of 10, 15. And here it is 15 comma 10. So in first case, value of m is 10, value of n is 15. And in second case, values are reversed. So beta 10 comma 15 minus beta 15 comma 10. We know that property of beta function that beta mn is equal to beta nm. And therefore, values of these two are same. Therefore, after subtraction, they get cancelled and we get final answer is equal to 0. This is as per the property of beta function. That is beta mn is equal to beta nm. Next example, show that integration 0 to pi by 2 root of tan theta d theta multiplied by 0 to pi by 2 root of cot theta d theta equal to pi square by 2. There is a multiplication of these two integration, and therefore we are going to solve these two integrations one by one. So let us take the solution. We are going to assume this first integration is equal to I1. So let I1 is equal to integration 0 to pi by 2 root of tan theta d theta. Now we are going to convert tan in terms of sine and cos, and root means power is half. So we can write down I1 is equal to integration 0 to pi by 2 sine raised to half theta upon cos raised to half theta d theta. Let us simplify it further by taking cos term to the numerator. So we can write down integration 0 to pi by 2 sine raised to half as it is and multiplied by cos raised to minus half theta d theta. We have already studied one standard formula, property of beta function in terms of sine and cos, that is integration 0 to pi by 2 sine raised to p theta into cos raised to q theta d theta. So according to that formula, we know that value of sine raised to p into cos raised to q is equal to 1 upon 2 times beta of p plus 1 by 2 q plus 1 by 2. So if we do the comparison, we can observe that value of p is equal to half and value of q is equal to minus half. And therefore, using this formula, we can write down I1 is equal to, so I1 is equal to 1 by 2 beta of 1 by 2 plus 1 upon 2 and minus 1 by 2 plus 1 upon 2. So here 1 by 2 plus 1 upon 2 means 3 by 4 and minus 1 by 2 plus 1 upon 2 means 1 by 4. And therefore we can say that I1 is equal to 1 by 2 times beta of 3 by 4, 1 by 4. Again by using one more property, that is relation between beta and gamma function. Beta mn is equal to gamma of m into gamma of n upon gamma of m plus n. We can take value of m as 3 by 4 and value of n as 1 by 4. So using that formula, we can write down gamma 3 by 4, gamma 1 by 4 upon addition of 2. 1 by 4 plus 3 by 4 becomes gamma of 1, and we know that gamma 1 is 1. For sake of convenience, we can write down 1 by 4 first. So 1 by 2, gamma 1 by 4, and 3 by 4 can be written as 1 minus 1 by 4. We are using the same concept whatever we used in our example number 1. So gamma 1 by 4 into gamma 1 minus 1 by 4 upon gamma 1. We have already found out the value of numerator in example number 1, that we are going to use it directly by using the formula gamma p into gamma 1 minus p is equal to pi upon sine of p pi, and that value was pi root 2. So 1 by 2 as it is, value of numerator is pi root 2 and gamma 1 is 1. So we are using the formula gamma p gamma 1 minus p is equal to pi upon sine of p pi, where value of p is 1 by 4 here. So in short, by taking the ratio of 2 and root 2, we can say that I1 is equal to pi upon root 2. Now we are going to solve I2, means second integration. So let us take I2 is equal to integration 0 to pi by 2 root of cot theta d theta. Now we are having shortcut to solve this I2. Why there is a shortcut? For that, we must know the property of definite integration. So consider the property of definite integration, that is integration 0 to a fx dx is equal to integration 0 to a f of a minus x dx. So if we compare with this, a is pi by 2, and therefore we can write down this cot as cot of pi by 2 minus theta in this manner. So 0 to pi by 2 root of cot of pi by 2 minus theta d theta. What is the advantage of doing so? Cot of pi by 2 minus theta is tan theta. And therefore, here we can write down 0 to pi by 2 root of tan theta d theta. It means that value of I2 is equivalent to that of I1. And therefore, we can say that I2 is also equal to pi upon root 2. Now we can say final answer, that is LHS is equal to I1 into I2. So if you put the values of I1 and I2, we get pi upon root 2 into pi upon root 2, and that is nothing but pi square upon 2. And therefore, this is the integration 0 to pi by 2 root of tan theta into root of cot theta d theta multiplied by second integration. Answer is equal to pi square by 2. So that is the answer, means in short we can say that is proved. Now we are going to take example number 5. Show that integration 0 to 1 x raised to m minus 1 1 minus x square raised to n minus 1 dx is equal to 1 by 2 beta of m by 2 n. Observe that integration limit is 0 to 1. There is no denominator. It means that we have to use definition of beta function. So definition of beta function we can see by definition integration 0 to 1. As I told you earlier, we can write down the definition in terms of any variable. So I am writing down in terms of y. So y raised to m minus 1, 1 minus y raised to n minus 1 dy is equal to beta mn. Now let us go for solution. What is the observation now? If you do the comparison, here in bracket, by definition, we should have a linear term in the form of 1 minus y. We should not have any power of the variable. But in example, power is x square. Means it's very clear that we have to do the substitution for that x square. So LHS, first of all, write down as it is, and in next step, we are going to do the substitution. So let us do the substitution, x square equal to y. Therefore, we can check the limits now. At x equal to 0, y equal to 0. At x equal to 1, y equal to 1 square, that is 1. In short, limits are unchanged. Value of x, taking square root on both sides, we get x is equal to root y. Now let us find out dx. So dx is equal to derivative of root y is 1 upon 2 root y into dy. And now we can do the substitution in the equation of LHS as the limits remain same. So therefore, LHS is equal to integration 0 to 1, replace x by its value, that is root y raised to m minus 1, multiplied by 1 minus y raised to n minus 1. See that x square is replaced by y, and now dx is 1 upon 2 root y dy. So it is 1 upon 2 root y dy. Now we are going to simplify it further. So 1 by 2 we can take outside. Integration 0 to 1. Now we know that root means power half. So root y can be written as y raised to half raised to m minus 1 as it is. Second term again to be written as it is. And now root y can be taken to numerator by writing down this as y raised to minus half dy as it is. Simplifying further. Now we are going to use laws of indices here. So keeping 1 by 2 as it is, integration 0 to 1. Now we are going to combine power of y term. That is y raised to m by 2 minus half minus half. In earlier bracket, we can see that in earlier bracket, it was y raised to half raised to m minus 1. So if you use laws of indices, here we get y raised to m by 2 minus half. And therefore, we can write down this as y raised to m by 2 minus half minus half. And second bracket, 1 minus y raised to n minus 1 dy as it is. Now we are going to simplify it further. That is minus half becomes minus 1. So integration 0 to 1 y raised to m by 2 minus 1. Second term 1 minus y raised to n minus 1 dy as it is. Now concentrate on definition. What is the change? Instead of m now, it is m by 2. n remains same. So this is the definition of beta m by 2 comma n. Because instead of m, there is only m by 2. And therefore we can say that integration 0 to 1 x raised to m minus 1 1 minus x square raised to n minus 1 dx is equal to 1 by 2. And this is as per the definition. We can write down m by 2 n in beta function. So that is proved. So this is all about examples on beta function. So thank you.